Hi, everyone. Can everyone hear me well? Cool. All right, so let's do this. Welcome to HashiConf. Schedulers have been all the rage for the last couple of years, and this talk is going to be about the role of schedulers in modern operations. I'm going to talk to you about how a scheduler can help you run web operations, and hopefully we'll provide some guidelines for evaluating different schedulers, what to expect out of them. And throughout this talk, I'm going to talk about mainly the problems that schedulers solve and our take on them and how we solve them in Nomad. So this is going to be a very use case driven talk. At any point in time, like if you have any questions, just like show up your hand, and I'm happy to talk about them. So I don't need to talk much about all the products that HashiCorp does. You are in HashiConf, so for the next 2 days, you will hear about all the things about HashiCorp and all our products. But this talk is going to be about Nomad. And I work on Nomad. I'm in the core team of Nomad, and before HashiCorp, I was an engineer in the platform infrastructure group at Netflix, where I worked on a distributed cluster scheduler powered by Apache Mesos for running containers on Amazon. And before that, I did like various platform engineering, SRE type roles at various other places. Um, so the main theme of this talk is like how do cluster schedulers help in scaling operations? So web operations, I think, have come a long way in the last decade. Like from writing custom scripts to doing Puppet and Chef, early 2008, 2009, we have come a long way. We are no longer talking about deploying a server or deploying a couple of servers using configuration management. We talk about deployment with respect to like clusters now. Like when we deploy something, we talk about deploying a whole cluster. When we are debugging something, we debug a whole cluster. So web operations have come a long way. We are not only deploying like tens of servers. Like if you're doing service-oriented architecture, you are probably deploying tens of services or hundreds of services based on your scale and architecture. And so the scale of operations, the scale of doing web operations has changed in the last, I think, like 5 or 7 years or maybe 10 years. So this is where I think cluster schedulers come into the picture. And this is why cluster schedulers have been so important in modern operations. 4 years back, like when I was working at a gaming startup in Los Angeles, like I remember writing my first scheduler. So it was the day like when we hit our game on App Store, and the day we launched, we became like #1 or #2 in the matter of 7 or 8 hours. And I remember like our ETL jobs, which processes like how many players were playing our games and making reports of our games, like were running fine until the time we hit the App Store. And the day we reached App Store, when we had like 1 million or more downloads in a couple of hours and millions of players playing our game, like our ETL jobs couldn't keep up, of course, right? Like we would have to basically like babysit our ETL jobs, and that's when like I started working with clusters, and it was to like scale our batch processing infrastructure. And the same thing happened when I was at Netflix. I was an SRE at Netflix, and I was seeing like Netflix already had a really good deployment story. And that's when, and even then, like it took us like 10, 15 minutes to deploy a cluster onto the cloud. And I was thinking like, what can we do next? Like, how can we reduce the 10, 15 minutes to like less than half a minute, right? That's when like I started working on like a deployment architecture based on Apache Mesos and a distributed scheduler for running Docker containers so that we can further reduce the time. And the theme, like throughout that journey of writing schedulers, has been to scale operations, right? Scale like how people are deploying and how people are rolling back, how people are putting new versions, running canaries, and so on. So I think the theme of schedulers, when you're introducing them to your organization, is about what you're doing today, how you can scale it from 1x to like 10x or 15x, right? So with that, I present to you like the role of schedulers and the kind of things that one has to keep in mind when one is evaluating a scheduler. And these are the things that I consider that a modern scheduler should do. And when I would talk through each of them and what we do, like some of the things we have done in Nomad, and I would explain like what we have done. And I would also explain to you like what we are going to do in the future about the things that we have not done so far. Uh, so, uh, so the theme here is that the role of schedulers again is to make the life of operators and developers simpler. For operators, it is like how do you do less maintenance work? Do like how do you do more of like rolling out new services, rolling out new nodes, rolling out new clusters, rolling out new data centers? The things which are very hard, like how do you do it easily with schedulers? For developers, the theme is how do you reduce availability concerns in your applications? How do you deploy your applications faster? So there are like two different use cases or two different kind of personas, if you want to say, when it comes to schedulers. One is the developer and the other is the operator. So we will see like how each of these things, like for example, fault tolerance and traffic shaping and resource utilization, like what do they mean for all these two different personas? For people who haven't heard about Nomad, I would like to explain what Nomad is first before going into them. So Nomad is a distributed cluster scheduler. It's multi-data center from the get-go. It's multi-region. It supports flexible workloads. It's made for large scale, like every other runtime tools at HashiCorp. And it's operational simple. Like if you have experience with HashiCorp tools, like you know that like we strive to make things easy. And like we saw like how other schedulers work, like having the experience of working on other schedulers. Like we had the late movers advantage in the space. We were like, okay, this is what everyone else is doing. Let's see what are the pain points of system administrators and engineers who are running schedulers in production, who are deploying applications in production. Like let's see how we can make the operational complexity simpler for a cluster scheduler that we are going to write. It's heavily inspired from research about distributed schedulers. As I said, like it's a concurrent and distributed scheduler. There are two types of schedulers mainly, and I'll cover them. Nomad is optimistic and distributed from the get-go. It does its own state coordination. It doesn't depend on an external service like Zookeeper or etcd for doing its state coordination. That makes it simpler operationally. And then it supports service and batch workloads. It's pluggable. Again, like this is something which is important to note here is, when it comes to schedulers, there are like two different camps. One camp is like, we are going to make the scheduler so extensive that you are going to write frameworks like you do in Apache Mesos, where you have very domain-specific schedulers. And on the other hand, like you have schedulers where it's very simple, and they say that you can plug in everything, and they present an API, and then you are basically plugging in advanced schedulers, advanced volume storage and things like that. We took the middle ground. We were saying like, let's see what people do most. People run mostly like services and batch processes. So we came up with like two really good schedulers for running batch processes and service workloads. And we said that if this is what people are going to do, let's make the experience really nice out of the box, right? And then if there are use cases which are in the 20% or 5% use cases, let's support plugins and things like that so that people can extend it if it doesn't meet their use cases. Scaling requirements of Nomad was like we wanted to support thousands of regions and tens of thousands of clients in every region. And we expect people to run like thousands of jobs in every region. This is not our first runtime tool. Before Nomad, we produced Surf and Console. And so like when we started Nomad, like we came with a lot of experience of doing distributed systems. Surf provided like a good way for us to, with Surf, like you could do like P2P, cluster membership. Surf uses Gossip, and we have seen Surf scale to like large number of nodes in production. We've seen Surf scale to like tens of thousands of nodes in production. And with Console, we had the advantage of knowing how a consistent service discovery system work, like which provides a consistent view of your whole infrastructure. And it's multi-data center from the get-go, and we know that Console is powering a lot of modern web in production, which are of large scale. So having done Surf and Console, we had the very mature libraries in the distributed system space, which were proven, and we knew like what to do. And we brought them together in Nomad, right? And the only thing that Nomad didn't have at that point was like a good scheduling logic, good semantics around deployment of software, and good maintenance primitives and things like that. And those are the things that Nomad now brings onto the table. So if you're already using Surf or Console, or if you know that Surf and Console works really well, Nomad is going to, it's going to take all that like one step forward. This is how a Nomad job looks like. We use the HCL language for defining jobs. So a user basically describes a job like this. The user specifies the data centers where the job has to be run, and the task and the resource asks of a task. I'm going to cover each of these like later in a bit throughout my slide. So next up is the data model. So the data model is like the fundamental, one of the fundamental aspects of a scheduling system. To understand like how a scheduling system works, like you need to understand like what is the data model behind it. And when users submit a task or a job or anything happens in the ecosystem, what happens is that is triggered to Nomad as something called as an evaluation. So any change in the system, which can be like a submission of a job, like submission of adding a new node into the system, or like a data center failing, or like a collection of nodes failing. All these are basically modeled as evaluation. And when an evaluation is bubbled up into the system, like we create a new allocation. And allocation is what represents the actual change that is going to happen in the cluster. So when you submit a job, like that's an evaluation, and evaluation is triggered in the system. The scheduler then basically churns the works on the evaluation, and an allocation basically represents the work that the system now needs to do. And every node which is running a Nomad client is now going to download the allocations and is actually going to run the processes. So you can think of evaluation as an function which the scheduler runs, and the result of the function is a bunch of allocation update. So when you submit a job, that can be an evaluation which can produce like thousands of allocation. And allocations is something that we have borrowed directly from other really high-scale schedulers. So basically, a allocation is something which embodies a running, like the data model which embodies a running instance of your job on a node. So if you have a job which needs basically like thousands of tasks, so in the cluster you can expect to see like 1,000 different allocations running of your job. And as I said, like we have a bunch of schedulers which are which come with Nomad out of the box. And the 3 schedulers that we have developed so far are service, batch, and system jobs. And each of these schedulers can run in parallel with each other. They don't need to all run on a single machine. They can work by themselves, and they can make independent scheduling decisions. And this is very important. So if you are an organization like who are running thousands of batch processes, which are not mission critical, but like 5 services, which are front-end services or API services which power your business, even though like you want to do some machine learning job or like run some batch processes which have like a really high number of count, because our scheduler is like highly concurrent and highly optimistic, and all of the schedulers are running in parallel, the batch processes, even if they are high in number, they won't take over the service scheduler. Like you as an operator can decide like how many schedulers or how many number of instances of schedulers you want to run on every machine. So that is really important. In most schedulers which are not optimistic and not concurrent, what you would see is like a head-of-line blocking. So when you have, during a time of a day when you are running lots of jobs of a different type, of a certain type, you will see some other type of jobs are not getting a lot of your scheduling time. So that's the fundamentals of how of the system. I'll cover more about how scheduling works later. So let's talk about fault tolerance, right? So fault tolerance is like the number one objective that people have in modern infrastructure. If you're running service-oriented, if you're running your application in service-oriented architectures, you are probably running like hundreds of services which power your businesses. And there is like so much going on, and you would obviously like want your service, you would want as many number of nines as you can get out of your system. And this is, I think, the first thing that cluster schedulers should try to solve. For example, when a node crashes, or like the cluster scheduler should restart the services. Uh, the cluster scheduler should handle hardware failures. Like when you have hardware failures, especially if you're on the cloud, like you are running on commodity hardware. If you're running on the cloud and you're using spot instances, for example, in Amazon, like those instances are not guaranteed to stay, right? Like you are not going to count on your hardware to stay forever. You would want like your underlying infrastructure to heal in a way where whenever the hardware changes happen, whenever hardware goes away, the overall system is still stable, the overall system is still available. And this is, I think, something that cluster schedulers should solve. Then not only just like hardware failures, like we need to think about data center failures. What happens when a zone in Amazon goes down? What happens like when there is a higher latency between two different zones? Like how does your infrastructure heal in that case? And that's another place where cluster scheduler should help. Like it should basically change the network topology of your applications, of your services, based on like how your data center is doing at that point, based on how your hardware is doing at that point. And the cluster scheduler, like I said, should spread services across different domains. And we have something called a restart policy. When something fails, like we use the restart policy to make sure things get back online. We restart things. We have things like delay and interval. What it means is that whenever we are restarting stuff, Nomad is introducing a jitter, and like it's going to prevent thundering herds. So if you run distributed systems, and if you run things like using Zookeeper, so what it means is that when services restart at the same time, like those applications, because there is now jitter introduced by Nomad, they are not going to hit Zookeeper at the same time, or your databases at the same time. So there is going to be enough time for your overall infrastructure to heal. We treat failures as recoverable and non-recoverable failures. Recoverable failures are things like download errors of your artifacts or intermittent software failures, and they are restarted with a delay and jitter. So when like your software fails because of an out of memory or something, like Nomad will restart it automatically. Whereas a driver error is something like a configuration error, like you have not configured Docker properly, or there is something wrong with the file system. When something happens like that, Nomad is not going to restart the job on the same machine at least, because there is no point of restarting, right? Like there is no blindly restarting a job if it's going to crash again. So we make a distinction between like all these two types of errors. One of the things that people don't talk about fault tolerance is service discovery. Service discovery is always spoken in its own context, but I think service discovery and fault tolerance are very related. In a dynamic cluster scheduler, where the topology of your network changes and your services are going up and down, nodes are going up and down, you need your services to be registering and deregistering from a service discovery solution. And Nomad provides the integration with service discoveries out of the box. So far, we have only integrated Nomad with console because the space of service discovery is again very fragmented. People use like Zookeeper and etcd in a very different mechanisms. For example, Twitter uses server sets with Zookeeper for doing service discovery, whereas others use HTTP API of etcd for doing service discovery. So we have, out of the box, we integrate with console, but it can be extended to work with other service discovery system as well. So as a developer, you can define like the services that your task exposes and the health checks, and then Nomad is going to keep them synced with console and run the health checks and so forth. And as things fail in production, schedulers fail too, right? So schedulers are not not something that never fail. So it's important to understand what happens when scheduler fails. So if Nomad fails, for example, your allocations, your jobs that you're running on your cluster are going to continue to run. And if the task is failing because of a recoverable error, Nomad is going to restart them. But if a node fails, then the tasks are not going to move around. And when the schedulers fail, Nomad is not going to accept new jobs. And the cluster membership is also not going to change. So until and unless the scheduler is back online and they are working properly, like you will not able to like scale out or like submit new jobs, but your existing network topology is going to be fine. Existing jobs are going to keep running. Next up is traffic shaping, and one of the things, one of the things that I see very common these days is multiple data centers are becoming very common. And if you are running on Amazon, you are probably distributing your load across multiple zones, and every zone being its own failure domain. Like it's very common for you to, when you are doing a deployment, to spread them across zones, right? So your cluster scheduler should also come up with that, and also should keep up with that. And in that regard, Nomad helps doing deployments across multiple DCs. So when you are writing a job file, you can basically specify the different data centers where your job is going to be running. And if you want even more higher availability, for example, if you want to be running your application even when US East 1 dies, like you are probably going to be running things in an active-active manner where you're deploying your services in US West 2, US East 1, and EU West 1, right? So then you have like more tolerance than just like having one region failing. In that case, like you want your cluster scheduler to be a point, like a control plane where you could go on and like deploy jobs in each of these regions. And Nomad makes it super easy to deploy jobs across data centers and across regions. And this is how we do it. A region is a single isolation domain, and you can have more than one data center in a single region. And if you're running console, you can run console in every data center, and then you can connect, you can basically like connect those console clusters across the WAN. And Nomad clusters across data centers are presented to you as a single cluster. And over the WAN, if you have different Nomad regions, you could connect them across the regions too. And a region is a single scheduling boundary, so if a scheduler fails, like you won't be able to deploy jobs in a single region, but you could be deploying jobs at the same time, like to other regions which are functioning properly. And a data center is a single pool of resources, right? Like when you are deploying, like you want to at least like say that I want 50 nodes of my service in a single data center, and I want like different number of nodes in different regions. When there is a data center failure, we move your services from one data center to another. So if a zone failure happens in Amazon, Nomad is going to move like your services from one zone, the zone which has failed, to a healthy zone. But if a region fails, Nomad is not going to move the services from one region to another. The reason why we didn't do it is because different regions have different characteristics, and also there is data gravity, right? If you're running a database, most likely if you're running like an ACID database, then it's probably you're not going to be replicating that database across regions. If you're running a distributed data store, right, sure, like you're going to be moving your data between regions. And also, like there are things like prices of instances differ based on which region you are. So the policies for moving work from one region to another is not so simple, and we decided that it's not worth spending a lot of time there. Instead, like we would want to make a control plane where the users can decide when and how to migrate workload from one region to another. So in a single region, the workload looks like this. You run Nomad servers in different data centers in a single region, and every clients, you can run a collection of clients in every data center, and those clients basically talk to the servers in their local data center, and if the server in the local data center fails, they talk to another server in that region. And within a region, state is getting replicated, so even if a server fails, scheduling can still happen as long as there is quorum. In a multi-region environment, like the servers in different regions, they discover each other over gossip. So users can connect to any Nomad cluster in any region, and they could be submitting jobs in another region. Within a single region, the replication happens by raft, which is also what we use in console. So the state is highly consistent, but across the region, we use gossip for doing discovery of different servers so that it can be highly available. So even if a region dies, and if everything dies in a single region, if you have 3 regions, the 2 other regions can still talk to each other. Operational insights is something very important. As an SRE who have worked on large-scale infrastructure, like I always value insights, and I always think insights is like the first thing that should be first class in a system like cluster scheduling. So in Nomad, we provide insights which aid in troubleshooting applications. We manage and expose logs, and we also show operational metrics. So you can find out the status of a job and see what allocations are running for the job by running the CLI command. You can see the evaluation status, and you can see what all evaluations that has happened when you have submitted a job, and what are the results of those evaluation. What are the allocations that were created out of that evaluation. You will see like things like task events, which will show you the timeline of a task. Like when a task was submitted, when a task was when the client started downloading the binaries of your task, when it started and when it restarted and everything. So if you have a Node.js application running for quite some time, like you can go and see like how it has been doing over time, when it was restarted, if there was any failure and things like that. Nomad helps in log rotation. So if you have an application which is writing to standard out and standard out, Nomad will do log rotation for you, and it will stream the logs to the client. We don't do any log forwarding yet, but this is something we're going to do in the future. So if you are running a Splunk or Logly or any other log aggregation system, you can just point Nomad to them, and all your logs that you run in your services are going to be there. Like you don't need to configure anything else, and you don't need to worry about them. If you want to turn off logging, you can tell Nomad that I don't want any logs, and there won't be any more logs until you need them. So you have a configuration like this, where you can say that the number of log files and the maximum file size. If you say that the number of files is 0 and max files is 0, and then Nomad is just going to turn off logging until you turn it back again. So since we were doing log rotation, we decided to expose a way where you can tinker with the logs, you can see the logs, and we said, why not make an API for you to inspect the file system? So if you are running an application and want to see the file system and want to tinker with it and see like what's going on, like you don't need to now SSH into the system. You can use the Nomad FS suite of commands to basically see your file system and see what is going on there. You can cat a file, you can stat a file, you can list the contents and so on. And then operational metrics. As I was saying, right, we provide resource usage statistics of a task. We provide today, like we provide the resource usage of a task. We provide the resource usage of a node. We tell you like how much disk pressure a node is experiencing, and we also forward the metrics to remote syncs. So what it means is that if you are running Nomad and if you have the Nomad agent on every node, now you don't need to run any other extra monitoring system for monitoring what is going on that node, and also for monitoring the tasks on that system. So as you see, like Nomad reports you the uptime of a system, which is a gauge, and then Nomad will report the resources used by the allocations, and what is the resource usage of the host, and the allocated resources. So sometimes what happens is you might see that the number of allocated resources is 256 MB or like 500 MB. And then you will see that the allocations are taking maybe like more resources if you are using some kind of deployment mechanism which is not containerized, right? So if you are using a deployment mechanism which doesn't impose any isolation, you might be seeing that all the tasks and all the allocations are consuming more memory than usual. So this gives you a bird eye view of like how that node is doing. We expose stats in a very detailed manner for a node. So if you have more than one cores, which is probably the norm, like you will see like the CPU stats for every core, and you will see like things like memory stat, like the total available memory, used memory, and for disk, like you will see like how much disk is used, what is the inode percentage, what is the usage percentage, and so on. So this basically like helps in doing system administrations and doing like day-to-day operations easy. For allocations, like you will see like what each of this task, the operational metrics for each of this task, like you will see, for example, for Redis, like you can see like Redis was using 13 MB of RSS memory, and it was using like 6 cycles of CPU. and it was, you'll see the port and IP address, and you'll see like how much time the process is spending in the system mode and in user mode. So if you have an application which is making a lot of syscalls, and if that's the bottleneck, you have like an idea of like what's going on by just looking at the Nomad stats. We have some really good semantics for doing application delivery. We allow people to do rolling updates, we have priorities, and the same deployment mechanisms that users would do for running applications on Docker, like they would do the same on, for example, if they're deploying a Go binary. And this is something that we thought was very essential. If you're an organization who is running applications in Docker and also applications in like Go binaries and things like that, and running things like Ruby on Rails, not everything needs Docker, right? Or not everything can be deployed without a container. So if you're an organization where you are doing various types of deployments, we thought it would be nice if you could have the same type of deployment semantics and same way of doing deployments across all the different drivers and across all the different types of workloads. So this is something Nomad tries to achieve. Like the job file is something that you define for any kind of applications, be it containers, be it Go binaries, be it like something which is not inside any container, inside any container containerizer. Nomad comes with job priorities. What it means is that you can define how much is the priority of a job. So based on that, the scheduler is going to prioritize which jobs gets most resources. So at the same, if two jobs were queued, one had more priority, Nomad is going to dispatch the job which is higher priority than the lower. This helps when you are running low on resources. So I was talking that we have a solid scheduler, and it makes things really fast. So I'm going to talk a little bit about that. So the scheduler in Nomad is concurrent, and it does optimistic scheduling versus pessimistic scheduling in most other schedulers today. It's completely event-driven. There is no head-of-line blocking in Nomad. What it means is that if as I was saying earlier, if you have like a lot of one type of jobs, like a lot of batch jobs and few service jobs are still going to get more, as much scheduling time they need, and they are not going to starve because there are more batch jobs. So when an external event occurs, like they create an evaluation, and that evaluation gets queued in a broker, and each of the servers can run multiple schedulers in parallel. And each of the schedulers basically gets the evaluations that are queued, and they make plans, the scheduling plans. And all the scheduling plans are made optimistically, and the scheduling plans which don't have any conflict, they go through, and they basically a plan is created, the final plan is created, and we create allocations for them. And since it's concurrent, it might happen that there are some conflicts in the scheduling plans. Those conflicting scheduling plans are again taken back, and the schedulers again rerun them, and finally those jobs go out as well. We don't see any, we don't usually see any conflicts in scheduling happening unless like the scheduler is really busy and the cluster is really busy. On an ideal day, like you shouldn't see any scheduling issues. So today, like, as Mitchell was saying in the keynote, like we introduced something called as the Nomad plan. So as operators, until now in most other schedulers, there is very low visibility of what is going to happen when a new version of job is being run. And this is something the Nomad plan helps. When you run Nomad plan for an existing job file, Nomad plan is going to tell you the changes that are going to happen in the cluster. So for example, in this, like the Nomad plan is saying that I upgraded Redis from Redis 3 to the Redis latest. And it's going to be like an update which is not going to be in place. So we are going to be destroying existing Redis nodes, and we are going to be creating new Redis nodes because you're changing the binary. So something like this is really important if you want some amount of determinism, if you want some amount of idea what the scheduler is going to do. On the client side, we support a lot of different OSs. We support Linux, we support Windows, we support Darwin. Support for Solaris and FreeBSD is coming soon. Um, uh, the, 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 the Nomad agent can fingerprint the host, and we have a pluggable architecture for doing drivers. The plugin architecture today is not exposed because we are still going through the phases where we are improving the system very rapidly. And once the system becomes more stable, we are going to expose the internal plugins system to developers so that they can extend that and write more drivers. But writing drivers today is very easy. We have seen community write drivers for LXC, for example, and they're running things in production. And drivers are what runs things, and they execute tasks and provide resource isolation. And these are the drivers that we have today. We have Docker, Rocket. We have a KMU driver, which allows you to run things on KVM. You can run Java jars and static binaries in a standalone mode under C groups. So as I was saying, system administration is super important to us. We treat system administrators as importantly as we treat end users who are running services. We wanted to make application delivery semantics between the ops and the normal application, the normal services very similar. So the same delivery, the same mechanism in which an application is going to be deployed onto the cluster, like a Ruby on Rails application is going to be deployed onto the cluster, we want system administrators to deploy monitoring agents and audit tools the same way. And for that, they need a way to target the whole cluster and not a few cluster. So that we bring something called as the system jobs. So with system jobs, you can target the whole cluster, and you can run things like auditing applications or monitoring systems or logging systems across your cluster. They're really good for running tools which has to be running consistently on all nodes. And whenever a new node joins up, Nomad runs those system jobs that are submitted automatically. There is nothing that needs to be done. You can just bring in new nodes which has nothing, and all of a sudden you'll see your sysadmin tools running in those systems, on those nodes. Nomad supports a few maintenance primitives. For example, if something goes wrong in the middle of the night, the easiest thing to do is drain that node. So Nomad provides a node drain command, where you can basically drain a node, and then the scheduler won't place anything new, and all the existing allocations running on that node is going to go on to other nodes on the cluster. Nomad provides a bird's eye view of the whole cluster. So if you want to do inventory management and things like that, node status is your tool. So node status would provide you all the nodes in a given data center. And if you connect them across regions, you can even see node status of compute clusters in different other regions. This is something that people often talk with schedulers, and I think is quite hyped up. And I wanted to bring that up, and I think it's still important. It's bin packing. People say that cluster schedulers are super important for doing for getting higher resource utilization. And I think that's super important, but I think the other things that we have discussed so far, fault tolerance, maintenance primitives, are also important. With Nomad, we do bin packing out of the box, so you should be able to see higher resource utilization. In all the jobs that I've worked so far, in all the places where I've worked so far, getting 80 to 90% utilization is really a myth, right? People say that when you run a cluster scheduler, you are going to reduce your AWS bills, and you're going to see 95% resource utilization. In reality, you will be happy if you see 60% or 65% resource usage. That's the amount of resource usage I think is possible in most cases. Because in the cloud, at least, most the instance sizes are not balanced based on your needs. For example, some will have more CPUs and some will have more memory. So even if you need more memory and if you need less CPU, you will be packed on a machine which is higher CPU and the amount of memory you need, but there will be excess CPU left. So if you see lower resource usage across one of your indices, don't feel unhappy. Report your statistics with the dominant resources. See what is the dominant resource in your cluster, and see if your cluster scheduler is going to bin pack and make sure that at least one of the indexes in of your resources are being highly packed. We are going to provide an API for the overall cluster usage, and that is going to help in auto-scaling. This is something people often request us to do, and Nomad is going to cater to that. So in the future, you will be able to auto-scale Nomad clusters by looking at the API for the overall cluster utilization. We recently did a benchmark and saw what does it take to run Nomad, like a Nomad on a large number of clusters and to run a large number of services in Nomad. So if you have run cluster schedulers before and if you have developed cluster schedulers before, like you will know that something like this takes at least like 1 year or 1.5 years to make them production ready and production hardened. But we didn't have that luxury because we are developing open source and we don't know the context and the scale at which people are going to run Nomad. So we decided to see what happens if we push Nomad, right, to the boundary where companies like Netflix and Twitter pushes in a matter of like 2 or 3 years. We decided to say that what happens when you run Nomad in a really large number of nodes and like push Nomad to the extreme. So we ran 1 million containers. And I'm happy to say that we scheduled 1 million containers and placed them and started them under 5 minutes. And while we did that, it was not it was not like super easy. Like we optimized so many things throughout the system. Like we optimized the RPC mechanism. We optimized how we store RAF logs on our disk. We optimized like how API responses are returned. So we optimized a bunch of things throughout our journey of running 1 million containers on Nomad. So a lot of times you might think that you don't need 1 million containers in production, but you might be rest assured that if you ever need 1 million containers, like Nomad should be able to handle that scale. And this is the timeline of the project. We started the project last year when, last year Nomad 0.1 was released. We came out with multiple platform support, and it came out with concurrent schedulers. We did distributed cron and system jobs sometime later. We did service discovery and health checks sometime towards the end of last year. And this year, we spent a lot of time optimizing our system for running 1 million containers. We did log rotation. And today, we released Nomad Plan and the resource usage APIs and advanced cluster bootstrapping techniques. And in the future, we are going to do a lot of newer stuff like persistent volumes and networking, preemptions, ACLs, secure clusters. We are going to integrate Nomad with Vault for accessing secrets easily. We are also going to support oversubscription and chargeback models. If you're running Nomad in your organization where you have different teams, in the future you'll be able to charge each of your teams for the amount of resources they are consuming. So the work we are going to do in the future is, there is a lot of work that we need to do, and the future is exciting. So that's pretty much it. And if you want to play with Nomad, download Nomad. Nomadproject.io is our website, and go to GitHub and talk to us if you have any issues or any future feature requests and things like that. Thanks.
Give it up for Tanu.